my name is Alejandro, and welcome back for day 47 of me doing the NeetCode 150 challenge. So today we're doing our second NeetCode medium brand search problem. Without further ado, let's get straight into it. Okay, today we get a NeetCode medium problem 875, Koko Eating Bananas. Okay, I like the name of this problem. I don't know if I've ever solved it before. I don't see like the solve button and so on. Okay, this will be fun. Koko loves to eat bananas. Me too, Koko, me too. There are n piles of bananas. The ith pile has pile I bananas. Okay, now we're talking. The guards have gone and will come back in 8 hours. Okay, we gotta get some bananas before the guards come see us. Okay, there are n piles. Okay, I want to grab that biggest pile. In 8 hours. Okay. Koko can decide her bananas per hour eating speed of K. Each hour she chooses some pile of bananas and eats K bananas from that pile. Okay. Are we not going to use like a heap here kind of a thing? I'm already trying to think how this is going to be binary search, right? You're going to binary search for like what, your largest values? Okay, can decide her bananas per hour eating speed of K. Each hour she chooses some pile of bananas and eats K bananas from that pile. If the pile has less than K bananas, she eats all of them instead and will not eat any more bananas during this hour. Koko likes to eat slowly, but still wants to finish eating all the bananas before... Oh, she wants to finish eating all the bananas before the guards return. Return the minimum integer K such that she can eat all the bananas within 8 hours. Ooh, okay. Maybe it is using some heap, but you binary search on the value of K. Okay. Let's see. Piles is equal to this, and H is equal to 8. Output is 4. Okay, so like 1 here, 2 hours here is 3, 2 hours here is 5, 3 hours here is 8. Okay. So essentially, yeah, this is the very same thing as the last problem, where it's like, you find like a lot of the K's will be falses and then eventually true, right? The max K. Okay. First of all. Like the best she can do is eat a pile per hour, right? She's got to pick a pile per hour. So ideally, is H always greater or equal to the length? Yeah, okay. H is always greater or equal to the length, so there is at least a solution, right? Okay. That makes sense. So the maximum K, right? So, and there's what? There's at least one pile, right? So smallest K is equal to 1. Largest K is equal to max of piles, right? Okay. I can already tell. We're just gonna binary search over these K's, right? So what do we want? We want to find. So it'll be a bunch of falses followed by a bunch of trues. So we actually do want to find not only just the leftmost index, that is the index that we care about. The only thing we got to be careful about is like with leftmost binary search, it'll return an index even if it doesn't exist, because it'll give you the index of where something should exist if it does not exist. Okay, so here we have a bunch of falses followed by a bunch of trues, right? Worst case, we can just do leftmost index is equal to float of infinity, and we do the same thing, right? So here. Now the only thing, right? What is the size of these? So piles.length is 10 to the 4, and this is 10 to the 9. So let's convert this. Okay. Log base 2. 2 to the power 15 is greater than 10 to the 9. Let's just check these things. So this is false. 25 is false. 45 is true. 35 is true. 32 is true. 30 is true. 28 is true. Nope. 29 is false. Okay. So 2 to the 30. So this is about, okay, like 2 to the 30. So if I do math, so base 2 of this, so it'll be 30 times 10 to the 4. So it's like 3 times 10 to the 5. That is very, very manageable, right? Because one thing I was going to say is like, you want to know like can eat, right? If she can get through all the bananas in there, right? So it'll essentially be like, you take the divide sign of each number. Yeah, okay. So leftmost index. While smallest K is less or equal to largest K, we'll say k is equal to smallest k plus largest k over 2. Right, there's like our left and right pointers, and there we go. Now we'll say, okay, check if can eat all bananas in k hours. In k bananas per hour. Right? So at k bananas per hour, I figure out how many hours it takes to eat all the bananas at a rate of k bananas per hour and check if it is less than or equal to h, which is when the guards come back. Okay. This is a cool binary search problem, right? It's like binary searching over a space of valid solutions and so on. Okay, I wish I've done this problem before, but this is a good fun problem. Koko eating bananas. This might be my favorite LeetCode problem of all time, just because this is a great setup to a problem. I wish more LeetCode problems were like this, right? Bring some fun and energy into the problems. Like, now I want to solve this, right? I need to help Koko. Like, what rate is Koko gonna eat her bananas if I don't help her find out what rate of k bananas she needs to eat that? You know? Koko needs my help. Koko needs our help. We gotta help out Koko. Okay. Koko eating bananas. All right. Okay, I'm having a little too much fun, but this is fun. Okay. So we need to figure out num bananas. Num hours is equal to 0 for pile in piles. Hours will be equal to, okay, so it's the number of bananas, pile, bananas, banana pile, divided by k bananas per hour. This is how many hours it takes her, right? But it'll be math.c of this thing, right? If it takes her, 0.01 hours to finish the last banana, it still, takes up that last hour. Otherwise, she has not eaten all the bananas. Okay, and here we'll do num hours plus or equal to hours. Is true is equal to num hours is less than or equal to h. Is true index is equal to this. If is true index, then we want to find the leftmost occurrence of a true index, right? So leftmost index is equal to min of leftmost index, as well as our k here, right? This is essentially our index here. Best k is equal to float of infinity. Best k is equal to the smallest between best k and our current k, right? And then this is a true index, right? We want to find the leftmost true. So if we found a true, we only want to look at stuff to the left of us. Okay, so r is equal to mid minus 1. In this case, is going to be our largest k is equal to mid minus 1. Else, we'll just say that our smallest k is equal to mid plus 1. But in this case, mid is equal to a k, and mid is equal to a k. Okay. So this takes O of n. This takes a lot of work. No, this is O of 1, right? So we go for every single pile. It takes O of 1 work. So this takes O of n work, right? And we'll do it over logarithmically over up to 10 to the 9 permutations, right? And this is around 2 to the 30, right? So if I do 2 to the 30 and 10 to the 9, right? This number is bigger than that, right? So let's assume that this is 2 to the 30, right? Because that's the bigger number. Then if I do binary search over that number, right, of possible k's, then I'm going to do at most 30 iterations of this binary search, right? Because it will be log base 2 of 2 to the power 30, which is just 30, right? And then for each of them, I'm going to do O of n work over the pile's length. So it'll be times 10 to the 4, right? Which is like, which is just 3 times 10 to the 5, which is allowed on LeetCode, right? On LeetCode, you can do up to usually 10 to the 6, sometimes 10 to the 7 operations. So here, this will definitely be a valid amount of operations, right? And so here, I wonder if we can do, you know, like assert, you know, that best k doesn't equal to float of infinity. And then return best k. Can we do something like that? Oh, equals, not equal equal. Okay, so this works. Let's submit. And there we go. We helped Koko. Okay. We can do a little bit better. So essentially, there's always a solution, right? So what this tells me, which makes sense because we saw that, you know, h is greater than the number of piles. So, you know, she can just grab the maximum number of bananas inside the total thing. You know, so that means she can finish one pile in 1 hour each. So since h is like, you know, greater or equal to, you know, the piles at length, therefore there's always a solution. So we can get rid of that, and we can also just do our handy dandy, you know, binary search here, right? So here we can actually just return smallest k. And I bet you this will work. Oh yeah, we gotta remove that since that just no longer exists. Okay. Yeah, so this works. Now we can just do this. Bada bing, bada boom. Num hours is equal to sum. For banana pile in piles. There we go. So I wonder what's faster. Is it faster? Because this I do a linear scan. Actually, okay, each of these will do a linear scan over piles. So this works out, right? Okay, I mean, this is technically, you know, constant time, right? I do a divide sign and so on. I wonder, it's like, okay, can I remember, because here I'm doing kind of slow, right? How are people doing this much faster? Are they just saying like, hey, this is like, you know, 10 to the 9 here and just submitting based off that? No, yeah, that makes my life slower, right? I'm going to do a linear scan every single time no matter what. How are people doing this so fast? I'm only at 40% here. 145, is it? Oh, is it just a little bit of deviation where it's like if I submit a couple times, it ends up working out? Maybe I can do less than? No, I can't do less than, right? Yeah. No, that's not gonna work. That's not gonna work because again, we want leftmost occurrence of something. Yeah, I definitely cannot do less than. Okay. I mean, I guess we're in this range and so on, but we're kind of, you know, we're hugging that standard deviation and so on. So I'm pretty sure, like, you know, this is a good solution. Okay, how are people doing this in 1ms though? Okay, that's actually freaky. Unless they pre-computed the result for like, no. Okay, interesting. Okay, not sure. Because, okay, like, the only thing I could think of, like, you know, doing better is, like, figuring out, just, like, k makes sense, right? Yeah. No, it just has to be this way. Like, I can't get rid of this. Like, this is just not going to work. Like, I have to do the ceiling. I mean, okay, this is it. We just submit. Okay, this is my final answer. No matter what. There we go. Okay, so we're just at 35% and so on. I guess like maybe we're a little bit slower than others. Maybe it's because they added more test cases. I'm not sure, but this seems like a good solution. So as always, in all my videos, I do a quick recap of how I was able to solve the problem. So for this one, essentially, all that I did is, okay, we want to find the best, you know, k for Koko. right? Which is K represents the bananas per hour that Koko eats. The point is that, like, the guards will come back in 8 hours, right? And there's a bunch of piles, right? And if she eats at a rate of K bananas, she wants to, eat very slowly, but she wants to still be able to eat all the bananas. So Koko's goal is eat all the bananas, right? But she wants to eat all the bananas as slowly as possible. So one thing we could do, right, is like if we have all these piles, we could take, the largest pile here, right, which is 11, and just be like, okay, Koko will eat 11 bananas per hour, right? Because in every single hour she can go inside of one pile and eat at a rate of K bananas per hour, right? And so here's like, okay, she could just do like, 11 and get through this pile, right? And then she get through this pile, since she eats 11 per hour, she finishes all of those, right? So she finishes all those and all of those. And since the number of hours for the guards to come back is always larger than or equal to the number of piles, then that means like, if Koko picks, the max pile and so on, that means like she can clear out every single pile in an hour. The guards will take greater or equal to the number of piles there are in terms of the hours that they come back. So there's always a solution where just Koko, like, grabs the largest pile, eats that up to that many bananas per pile, and therefore she can clear out every single every single individual pile in just an hour each, and that's like, the best that she can do. But the point is that Koko likes to eat her bananas very slowly, right? So it's like, okay, that is technically a valid solution that will work, but she wants to minimize the bananas per hour eating speed, but just enough so that she still eats every single banana. She loves her bananas. She wants to eat all the bananas that she could possibly have. She wants to eat all of them, but she wants to do it as slowly as possible, right? So essentially, we know that, like, okay, either Koko, there is a valid solution. If she just grabs, like, the maximum pile of bananas and she makes that her eating speed, we know there is always a solution, right? So we know, like, anything larger than that speed does not matter, right? Because we now have like a theoretical, like, speed that, will guarantee a solution. Now, the smallest possible solution that could exist, if it exists, we don't know if it does exist, is she literally eats 1 banana per hour, right? So the literal, like, smallest number of bananas per hour that is just, like, greater than 0, right? If she eats 0 bananas per hour, she will never eat any bananas, so it's always false, right? So the smallest possible rate she could eat things is a 1. The largest possible rate that we care about that she can eat things is the maximum value of piles, because, again, anything larger than that, yes, will work, but again, she wants to minimize her speed, right? So we know that this for sure will guarantee a solution. We don't know if 1 will give us a solution. So what are we going to do? We essentially have a left and right bound, and we want to find, the smallest occurrence that is still valid. So essentially, it's like, from 1, we're going to have a bunch of falses, right? Like K is equal to 1 might be false, K is equal to 2 might be false, K is equal to 3 might be false, on and on and on and on. We know that when we get to the largest K, which is equal to max piles, we know that this guy is a true, right? Like, she can finish all the bananas in enough hours at this rate over here, right? So here she might not be able to finish them all at a specific rate, here she might, and so on. So at some point in the middle, essentially, it would have flipped from a false to a true, right? From, like, there exists some K in the middle between there, where it's like it flipped from she couldn't get all the bananas in time to she could get all the bananas in time. So what's the perfect algorithm here in order to do that? Well, binary search, right? We essentially have a bunch of falses followed by a bunch of trues, which is essentially a sorted array. If you think of false as 0 and true as 1. And so you want to find the leftmost occurrence of a true. Why? Because a true essentially represents that she can get through all the bananas enough time. And, like, the indices, like, represent, like, the eating speed. So the leftmost occurrence of a true is essentially the smallest possible K, such that it is still true, meaning that she can still get through all the bananas, right? So we're essentially going to binary search through all these values, and so we're just going to keep going through K's and so on as we go on. And then how do we determine if a K is a legitimate one or not, right? Well, we're going to compute the number of hours it would take for her to get through all the bananas at a specific speed rate of K, right? Where K is always the midpoint between the smallest and largest K that we see so far. And all that's going to be is like, okay, for each pile, we're going to say, okay, for example, here there's 3 bananas, and let's say that our K is equal to 1 here, then it'll be 3 divided by 1 will take 3 hours to get through this entire pile, right? So that's essentially how we do it. And let's say that, she gets through the pile in 2.5 hours. Well, she can only go to a pile every hour. So if it takes her 2.5 hours in order to finish a pile, really we'll say that it takes 3 hours, right? So it'll be math.ceiling of everything, right? Because she wants to clear out every pile because, again, she wants to eat every single banana that is there available. So she must, account for that, and like, you know, if it takes, you know, a fraction at the end of an hour in order to finish up all the remaining bananas, we still count the full hour for that. So for every single pile, essentially for every banana in piles, we're going to divide the number of bananas by the rate that she's currently eating them at, take the ceiling of that in case, you know, there's still a fraction of an hour that she requires, and take the sum of that for all the piles, right? Because essentially that'll give us the total number of time it'll take for Koko to clear out all of the bananas at this specific eating rate of k bananas per hour, right? And then we say, okay, this is the total number of hours it takes for Koko to get through all the bananas. Is this in less than or equal to time than the time it will take for all the guards to come? Well, all the guards will come back when after h hours, right? So if the number of hours it took Koko to eat all the bananas is less than or equal to h, then great, right? This is a valid solution. So here what I used to have is like, you know, the best k, and I said like here is like, okay, best k is equal to the minimum between, you know, the current best k and the current k eating rate that we have here. And then, and you know, best k I did initialize it to like, you know, infinity, whatever, and so on, or, you know, max piles and whatever, and like this would always work, and here I'd return best k, right? Here I'm just kind of leveraging leftmost binary search. But, you know, I might as well make an example of this. You know, best k we'll say is equal to largest k because we know that largest k works, and here we'll say best k is equal to the minimum of that, and here at the very end we return best k, right? And if I submit something like this should still work. Right, so this still works, 37% and so on, because it's like, okay, here's a valid solution. So every time I see a valid solution, I will update my best k to be, you know, the minimum that I've seen and the current k, because we know this k is a valid solution, right? Starting with the largest k, because we again know that this is a valid solution straight off the bat, right? And then if we see a valid solution, then it's like, okay, we have found a k where Koko can get through this, right? So we're not interested in any k's that are larger than us, right? Because again, we want to minimize k. So we're only interested in k's that are at least this k, because we know that this k is valid, and things that are smaller than us, right? So that's why we look in the left subhalf. So we're going to cut down to the largest k now to be k minus 1, right? We keep track, okay, this current k might be a solution. Who knows? Unless there's, you know, any smaller k's that are also valid. But now we're going to look in the left subhalf, which is why we cut down the largest k to come down to k minus 1. Otherwise, it means we still haven't found a solution. So these k's are too small, right? And in that case, then it's like, okay, let's keep searching in the right subhalf to then find, you know, the smallest k inside of there, right? Because if our current k is too small, anything that is even smaller than me is also too small. So let's look in the right subhalf and so on, right? But then I don't use best k here because again, with a nice property of leftmost binary search is that, you know, essentially the left index here, which is my smallest k, will always give you that essentially like leftmost index, and if the leftmost index does not exist, right, if no solution exists, it will give you the index of the of where the solution should exist if there was one, right? In this case, since we know again that, you know, the number of guards is greater or equal to the pile's length and so on, we know that this, for example, is definitely a solution in the first place. So the smallest index will always be a valid index and so on. So that's why I don't make any asserts and so on, and I can just return it right off the bat, right? But otherwise, if that doesn't make sense, you can just do, you know, like initialize your best k to, you know, the maximum possible value. And then, like, you know, every time you see a valid solution in here, then it's like, okay, update your best k between the minimum, between the current best k and the current k that you see, and so on, keep binary searching until you've exhausted everything, and then at the very end, return the best k that can do that. If that helps you think about the problem better, then you can absolutely do that, and there you go. But otherwise, you know, hopefully that explanation made sense. Essentially, it's like, you know, you binary search over, like, you know, the theoretical minimum k that, like, Koko can eat, which is probably invalid, and then here's, like, you know, a value that, you know, Koko can definitely get it through all the bananas in if she were to pick this rate, and then binary search to find, you know, the smallest index, which is essentially a bunch of falses followed by a bunch of trues. So you want to find the leftmost occurrence of a true, and so you just keep binary searching your way through, and then for each one, it's like, okay, you grab a current k, which is the midpoint between the smallest and largest, see if the number of hours it would take her with that k eating rate of bananas per hour, if she'd be able to clear through all the bananas in less than the number of hours that the guards would come back. And if so, then great. Then keep looking in the left subhalf, otherwise look in the right subhalf, and at the very end, you know, just return the smallest k, because with leftmost binary search, that will always be the valid index. Otherwise, again, just use the best k thing in case that helps you think about it better. But otherwise, that's pretty much it for the explanation. So hopefully that makes sense, and let's make sure that we check off the fact that we did this problem. So there we go, check mark green. And yeah, but otherwise, that's pretty much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I'd highly appreciate if you left a like or a comment. And otherwise, I'll catch you in the next one. So until then, ciao, ciao, my friend. Bye-bye.